The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I'd like to introduce Andrea Soligon from Fosters & Partners. He's a partner at Fosters & Partners from London, UK. He flew in to give this presentation, and I'll leave it up to you.
Thank you. Good afternoon, everybody. It's a pleasure to be here today to give this presentation. I'm going to give a brief overview of the performance-based seismic design of the new terminal at the Panama City Airport. I'm a structural engineer with Fosters & Partners. We are an integrated architecture and engineering design practice based in London, in the UK. And for this project, we provided full structural, architectural, and mechanical design services from the beginning of the project and all the way to construction administration. The owner is the airport authority, Tocumen Aeropuerto Internacional. Our client and design and build contractor is the South American and global construction company, Constructora Norberto Odebrecht. And we often collaborate with the San Francisco office of SGH, and for this project we retained them to carry out 2 critical analysis and design tasks, and the engineer of record is Ramirez and Associates from Panama. Tocumen Airport is one of the busiest airports in Central America, and the new terminal, currently under construction and near completion, will add 20 gates to those of the existing terminal for an additional estimated capacity of around 15 million passengers per year. This is an architectural rendering of the terminal. There are 2 symmetrical wings that extend from the center of the building, and they're covered by a doubly curved roof, which gently rises towards the center of the building. So from visualization to reality, this picture shows the status of construction in the field as of several months ago, with the primary structure complete and the finishes being installed. The building has a total area of over 860,000 square feet, and it's over 2,000 feet long. Because of its length, we decided to divide it into 5 independent structures via 4 seismic joints to mitigate the effects from temperature variations and relative seismic displacements. And the lengths of the different independent structures vary between 370 feet and 440 feet, 540 feet. Panama is located in a relatively high seismic region with seismic hazards somehow comparable to that of the west coast of the US. So seismic design considerations govern the structural design. The building was classified by the owner as an essential facility, and the seismic design category is D, according to both the Panama Building Code and ASC 710. I should say that the Panama Structural Building Code is based on an earlier version of ASC 7 for loading and refers to ACI 318 for the design of concrete members and to ASC for structural steel design. We retain URS from Pasadena to carry out probabilistic seismic hazard assessment studies and to provide site-specific response spectra and ground motion time histories, which were spectrally matched to the site-specific spectra. This slide shows a couple of site-specific spectra, horizontal and vertical spectra, for various return periods, which we use for one of the 5 independent structures. The project was delivered using the fast-track system with an aggressive schedule. We released the first set of foundation construction documents for one of the 5 independent structures only 3 months after our appointment and the project kickoff. And then the first piles for that structure were installed only 5 months after the project kickoff. And then for the next year or so, we released structural construction documents, package by package, about every 2 weeks to allow continuous progress in the field. The fast-track delivery was actually very challenging, especially in combination with the performance-based seismic design approach that we adopted. And close collaboration with our contractor and client Odebrecht was essential during both the overlapping design and construction administration phases. And I would say also, as well as having an integrated design team with architects and engineers in the same office. So next, I'm going to give a very brief overview of the structural systems, starting from the foundations. The foundations consist of cast-in-place drill shafts socketed into the rock, and the rock is about 65 feet below grade. There's typically one pile per column location, and the pile caps are interconnected by a grillage of gray beams to tie everything together and provide base fixity to the superstructure. This is a closer view of some of the gray beams during construction. The superstructure across all the 5 zones of the terminal is framed entirely in concrete up to and below the long span roof, and we chose concrete to take advantage of the good skills and experience of the local labor pool. So for this project, concrete was really an obvious choice for us. We tried to prefabricate the floor framing as much as possible, and all the precast members were fabricated locally. And we also took advantage of unbonded post-tension construction, which is very popular in Panama. Most of the floor framing is given by precast, pre-stressed double T decks, topped with a cast-in-place diaphragm and supported on cast-in-place concrete beams. Where the beam spans exceed 60 feet, the double Ts are supported on unbonded post-tension girders, which are indicated in blue in this diagram. The typical span of the double Ts is about 30 feet, but then the span is doubled to 60 feet in the central part of the building, where we essentially have most of the structural bays, which are as large as 60 feet by 60 feet. This picture shows the concrete superstructure nearly complete and prior to the erection of the long span steel roof. The seismic force resistant systems in the concrete superstructure below the roof typically consist of ductile reinforced concrete moment frames, and we chose moment frames to allow maximum flexibility to the architectural layouts and the baggage handling systems, which are always key drivers in airports buildings. There's also a limited number of shear walls only in Zone 3, the central part of the terminal. And all of the ductile concrete moment frames and the shear walls were detailed in accordance with Chapter 21 of ACI 31811. This is a shot during construction of Zone 2A at one end of the terminal, and here is another shot in Zone 3 in the center of the terminal. I'll talk very briefly about the steel roof, as it does have an impact on the design on the concrete structure below. This diagram shows half of the roof plan, and the roof structural systems comprise primary beams, which are shown in red in this diagram, and run along the perimeter and the longitudinal direction. These are tubular members spanning about 60 feet between concrete columns, and they are faceted on plan and on elevation. And then there are secondary beams which span in the transverse direction, and these are white flange plate girders. And then the systems are completed by an unfilled metal deck that provides a diaphragm, by tertiary beams that laterally brace the secondary beams and deliver the restraint forces to a series of roofing plane bracing systems. In this picture, you can see the concrete columns supporting the tubular primary beams, which are then supporting the secondary white flange plate girders. The transition between the concrete columns and the primary beams, the tubular beams, happens via a short steel tubular stub. This framing system, which was required to achieve the architectural design intent, is unconventional in that the secondary beams in the transverse direction do not frame into the columns. So under lateral loads in the transverse direction, the roof structure acts like a moment frame due to the torsional stiffness of the primary tubular beams, but it is not considered a moment frame from the seismic response point of view. And it's not one of the pre-qualified seismic force resisting frames listed in Chapter 12 of ACE 7. And in the longitudinal direction, the roof structure is a moment frame, but the beam to column moment frame connection between tubular members are not pre-qualified to a C358. So the longitudinal moment frames can only be classified as ordinary moment frames, which are not permitted in seismic design category D under a prescriptive design. And this is an architectural rendering of the interior space with the bottom flange of the roof secondary beams architecturally exposed and not framing into the columns, as I described in the previous slides. Now, moving on to the seismic design, rather than following a conventional code prescriptive approach, for this project we follow the performance-based seismic design approach. And that was to meet the owner's brief that specifically required to maintain operational continuity following an occasional earthquake. And because the seismic force resistance systems, as I described earlier with the secondary roof beams not framing into the columns in the transverse direction, do not conform to the types listed in Chapter 12 of AC7. And along the longitudinal direction, the roof steel connections with tubular members are not pre-qualified to AC 358. So, as permitted under Chapter 1 of AC7 and the alternative materials and design provisions of Section 104.11 of the International Building Code, we set up a design criteria which was based on ASCE 41, on the Pier Tall Building Initiative TBI document, the 2010 version, and the Los Angeles Structural Design Council document. And very important to mention that the design criteria, as well as the structural calculation drawings and analysis models, were peer-reviewed and accepted by a peer review team. This is critical for all performance-based seismic design approach projects. After careful consideration of the owner's requirements, we adopted qualitative performance objectives corresponding to 3 levels of earthquake shaking. The 3 objectives are operational under occasional shaking with a 72-year return period, immediate occupancy under rare earthquake with a 475 years return period, and life safety under MCE, maximum considered earthquake. The seismic criteria also included quantitative acceptance limits, both at the global level and at component level. At global level, under MCE shaking, we set the maximum story drift at 2% for moment frames and 1.5% for shear walls. And as I described earlier, the connections between the structural steel roof members are not pre-qualified to ASC 358 for special steel moment frames. So the roof has limited ductility capacity. And the fast-track project schedule didn't allow time to go through a connection testing program. So we applied capacity design principles and introduced an innovative fuse detail at the top of the concrete columns to ensure that the roof remains essentially elastic. The column vertical reinforcing bars are locally reduced in size to create a weak zone between strong segments where controlled plastic hinging and energy dissipation can occur. The blue bars in the sketch on the left-hand side diagram shows the weak zone, and the red bars show the strong zone. The reduced bars are spliced with 2 rings of type 2 transitional mechanical couplers to create the concrete equivalent of the dog bone connection or the RBS connection for special steel moment frames. By reducing and tuning the flexural capacity at the weakened segment of the top of the concrete columns, top of the roof concrete columns, we limit the maximum seismic demand that can be transferred to the roof, which allowed us to design the roof to remain essentially elastic. And the seismic criteria also included quantitative acceptance limits at component level. Based on the PRTBI 2010 document, we classified all components as either deformation or force control components. We selected as deformation control components flexural yielding in the moment frame beams and plastic hinging in the concrete columns at selected locations in the columns and at the base of the shear walls. The acceptance criteria under MCE shaking for these components is that the plastic hinge rotation is less than the life safety limit in ASCE 41, and we classified as critical force control the structural steel roof and anything which has to do with shear in concrete. And then we carried out a strength design with the demand taken as the MCE demand from nonlinear analysis and amplified by a factor of 1.5. But in all cases, the demand was limited to the maximum demand that can be delivered to that component. And then so that's the demand. And then the capacity was taken from the code using expected material properties and the phi factor according to the code. And then as non-critical force control components, we selected flexure in the PT girders, foundation, diaphragms. And in this case, the demand was taken at the MCE demand without any amplification, and the phi factor was taken equal to 1. The use of nonlinear analysis is essential to performance-based seismic design, and under rare and MCE shaking, in this project we used the nonlinear static pushover analysis method, which is applicable in principle for low-rise buildings, such as this terminal. However, for the independent structure in the center of the terminal, we had to use the nonlinear response history analysis method, because that structure had a more complex response and it lacked a fundamental mode along the principal directions. And our friends at the San Francisco office of SGH carried out the nonlinear response history analysis for that structure. In terms of modeling for nonlinear analysis, the concrete columns were modeled as nonlinear elements with zero-length plastic hinges at the column ends and at the location of the ductile fuses at the top of the roof column. The PMM yield surface were calculated using the fiber cross-section with expected material properties, and the parameters of the backbone curve were taken from ASCE 4106, including supplement 1. Similarly to columns, the concrete moment frame beams were modeled with lamped plastic hinges at the beam ends, and the parameters of the backbone curve were taken from table 6-7 of ASCE 41. And the shear walls are modeled using shell elements with, coupled with the inelastic vertical fiber elements to capture the PM interaction and nonlinearity. The fiber element comprised steel reinforcing and the concrete with the stress-strain distribution as shown in the diagram. And then we added rotational gauges and axial gauges at the base of the shear walls to measure the plastic hinge rotation and the tension and compression strains in the walls. And we also had acceptance limits for the strains, even though I didn't list them in the previous slide. All of the force control members and actions were modeled elastically. And again, these components include the PT girders, the structural steel roof, and the diaphragms. In the interest of time, I'll just show a couple of results from nonlinear analysis. And this slide shows a sub-2000 model of one of the independent roof structures and the end of the terminal, for which we carried out a pushover analysis. The plastic hinges are lamped at the column base and at towards the top of the roof column, at the ductile fuse in the area indicated in green in the closer view of the diagram. This is the deformed shape and the plastic hinge pattern from the pushover analysis at the performance point corresponding to MC shaking. The color coding indicates the damaged state in the plastic hinges, and in this case the pink color indicates the immediate occupancy performance, which is a lighter degree of damage than the performance objective of life safety under MC shaking, implying in this case that the columns have achieved a satisfactory performance at component level. And these are a couple of pushover capacity curves with the loading in the longitudinal and in the transverse direction. The performance points for the three levels of shaking intensity are indicated along the capacity curves, and we can see that under the occasional earthquake, the response is completely linear elastic. Under rare earthquake, we are just beyond the linear elastic limit, and at MCE, we are into the nonlinear range, and the story drift in this case is just about over 1%, which is less than the limit of 2% that we picked. For this independent structure, in order to validate the pushover analysis, we also carried out a nonlinear response history analysis, and the results between the two analysis methods compare well. In this instance, the roof displacements from nonlinear response history analysis are also around 1%, which is same as the previous slide. These are some sample results from nonlinear response history analysis of the structure in the central zone of the terminal. We use 7 sets of triaxial MC ground motion time histories, and the peaks of the various response parameters from the 7 ground motions were extracted, and the average of the peak values were calculated for performance evaluation. In this case, the maximum story drift for the roof columns, which are indicated on the diagram on the left-hand side, is also about 1% and less than the limit of 2%. And this diagram, although the text is really too small and it's not really legible, is meant to show the plastic hinge rotation demand capacity ratios for the columns. And in this case, the DCR is at 0.55. And similarly, we check the performance of all the other deformation control components, such as the plastic hinge rotation in moment frame beams, shear walls, and the coupling beams. So in summary, this project shows that performance-based seismic design is increasingly being used by structural engineers to meet the requirements of owners who are demanding a better and more predictable response for their buildings. It's being used to meet the design intent of modern architecture, and in this case to provide a solution for a complex and non-code prescribed lateral system. And it also gives engineers opportunities to introduce innovative solutions such as the ductile fuse at the top of the roof columns that protect the structural steel roof. And it's also increasingly being used outside of the US in developing countries. I'd just like to say that the terminal is scheduled to be open next spring, and we are looking forward to that. So thank you for your attention.
We have time for a couple questions if you want to entertain some questions. Any questions?
We have time for two. I have a question regarding the pipes. What type of model you have done for the foundations?
Yeah, so we designed the superstructure as fixed, and then we applied the reactions from the superstructure to foundation models where the soil structure interaction was, analyzed using the PY curves method.
So the pushover was done with the fixed model?
Correct, yes, for the superstructure, yes. And then we designed the foundations with different models.
I guess it was a matter of time.
Yes, yes. As I mentioned at the beginning of the project, we really had to hurry in the design, and I'm not sure that in future projects I'll be looking forward to doing fast track in combination with performance-based seismic design. It was a matter of time, yes.
Okay. Thank you.
Thank you.